fins, axial drag. So, you know, the most difficult, quotes, part of drag is Fleaman messes up with the imperial units, and it's a mess, and you know it induces me so many headaches. You know, because when you simulate something and it doesn't make sense because you have, well, an analytical solution to compare with, and it's order of magnitudes different. Well, you got to start debugging and you got to start plotting. Well, let's see what can be wrong. What can be, have I messed up some equations or whatever? So, and I was messing up the axial drag. So what I did is I just plotted out the different drags. So the drags due to the fins, the friction, fins, wave, fins, pressure, blah blah blah. And I'm pretty sure it was fins. There was one drag that was, you know, enormous in orders of magnitude, like 0.2, 0.3, one component of the drag. You know, the overall drag of a rocket is going to be maybe from 0.3, maybe the higher 0.2s to 0.45, maybe in the transonic regimes. It's going to be this order of magnitude. And yeah, if you have something outside there, well, you're messing up with imperial units. Congratulations. You know, we've lost so many money due to imperial units. I think there was a NASA mission that failed due to the subcontractors that used imperial units, and they were sending them in, you know, in imperial units, and NASA thought it's a national system. You know, a lot of millions have been lost. A lot of headaches could be prevented. But anyhow, I have correct in this section. I'm using again Fleaman's models, but I have corrected for you all his equations on international system units. So you have to be careful, as I told you before, if you have non-dimensional parameters. Like, imagine if we had an equation where, well, the aspect ratio appears, or maybe the length of the rocket and the diameter. Well, this is non-dimensional. You can put this in you know, inches or footlongs or whatever. It's gonna be non-dimensional. The aspect ratio is non-dimensional. The problem is when, you know, if you have a dimensional variable hanging over there, like dynamic pressure, and if it's in slugs per inches per whatever, well, it's gonna mess up. So that's the only thing you have to worry about. But I have you covered, because I'm gonna present all the equations in international system. So fins and drag. Fleaman doesn't, as I told you before, he doesn't put the pressure term. I believe Open Rocket does. You can check that if you want. So let's start with the friction, the skin friction. So it's gonna look like this. Right. Also careful on how I define, for example, n, which is the number of wings or the number of fins. So remember, wings is, Fleaman defines it like a pair of fins. So if you have 4 fins, you have 2 wings. I will define n as number of fins. Okay, I think it's easier. And plus, if you have 3 fins, well, you don't have to put, you know, fraction, which doesn't make much sense to me. So I don't know if I'm gonna put all the subscripts, because friction. Yeah, last time I'm doing this. let's see, it's proportional to the number of fins, S surface, which we defined before. Did we put A? Yeah, I'm gonna be consistent. Remember, this is the reference area, so yeah, pi over 4, diameter of the rocket squared. Then we have a constant which comes from putting the variables to proper units. Then I believe it's 2, 3. Let me check. Okay, that's right. And then we have this term here, which is a dimensional term. Dynamic pressure and the mean aerodynamic chord, Mach number, power 0.2. So the mean aerodynamic chord, well, we won't have space if we put this arrow like this. I'm just gonna write it here. The mean aerodynamic chord for this is only valid for trapezoidal fins. Is 2/3 the root chord squared tip root plus tip squared, and over tip plus root. Remember, this was the chord of the root and this was the chord of the tip. Okay, you could put the taper ratio. Sometimes they use this variable, which is just the ratio from the, from the roots and the tip. Yeah, I don't. If they're not necessary, I just prefer not to add some more variables. So we just leave that alone. We'll just leave it like this. Okay, this is for the friction for the fins. We didn't have pressure. We were only missing the wave drag. So, wait. So for the wave drag, we have the following expression. Alright, I paused the video. I didn't want you to sit there when I was writing it down. So a little bit longer expression. Again, I did some corrections here. If I recall correctly. Yeah. So n is the number of fins. Then we have a few new variables we haven't talked about. This is the square of the Mach. Let's define this. Well, we have to define a few things here. Let's see. Let's start with the leading edge. So LE stands for leading edge. Leading edge is the edge that which touches the air first. Let's say this leading edge. And let's see. Okay, so we define the sweep of the leading edge. So this is red. Sweep of the leading edge, sweep angle of the leading edge is this. And then the Mach, I don't know what name to call this. It's just the Mach number times the cosine of the sweep angle of the leading edge. Okay, so when you see this squared, well, it's this squared. What else? Okay, this is the angle. Let's say the if we take a look at this fin, This is where the air flows. So this is the leading edge, and this is like the tail. So this point here would be this point here. This is like the cross section of the fin. Okay. So if we have let's see. Let's get another color. This angle here, small delta leading edge, it's the angle from the this horizontal to here. So if we had delta leading edge 90, we'd have like rectangular fins. So as you can see, this term is squared. So this term is sine squared. Sine squared is like a parabola kind of. So this means that if this leading edge angle, no, this is, yeah, how does Fleeman call this? I think he just calls this like the tip of the angle of the tip. Well, if this angle, we'll call it just delta leading edge, if it's very large, this is a square term. We're gonna have a ginormous wave drag due to the fins. So we're gonna want to get this down and have a sharp edge. So I believe what it's normally done is the ideal for supersonic wings is something like this, like Rome, but for structural reasons, well, you just give it a small angle here, so it's not so bad as this. Oh yeah, and this is the thickness of the mean aerodynamic chord. I think it's self-explanatory, just the thickness, but at the mean aerodynamic chord. And yeah, well, this is a span and the reference area, and that's all there is to say. Well, we could do a quick analysis. We can see here that the influence of the sweep angle. Yeah, I forgot to mention that. I was about to finish. No, this is important. Sweep angle is critical to get down the wave drag in supersonic vehicles. There's a cosine term here. So we want to get this angle as large as possible. Yeah, that's right. As large as possible, and because you can see the influence here. So that's why on supersonic vehicles you're gonna see this angle pretty large. The downside to this, well, downside would be you're gonna have to make them longer, unless you want to cut it out. Then you have a lot less, way lower mean specific chord. So you're gonna have to make them longer on the other side still if you want to maintain the same amount of fins. But yeah, you can see that angles of, I don't know, 40 degrees are typical for the sweep angles, and yeah, you wanna get that up for supersonic vehicles and get this as low as possible. As you can see here, it's a big influence, and yeah, there's not much more to say. You can't touch much this one, the thickness of the mean aerodynamic chord. That depends on the structural restrictions. So you can play with these two angles basically. Okay, the leading edge sweep angle, the leading edge, and tip angle.